Okay. So the principle of uncertainty was first discovered not by any mathematical proofs such as these, but rather experiments, and they had to refine their values over time, and once those constants were refined, they then were able to make the mathematical proof. But what's funny is that you only need the basic ideas of Hermitian matrices to derive this relationship. You didn't need any of those experiments. And what I think is fascinating about this problem is that how we were something that could have been discovered mathematically beforehand that described the world, they had to struggle through all the experiments first to get there and then discover the proof for it. And it's a really elegant proof. So basically, I'm just going to introduce you to some of the notation up here. We have the change, basically the expectation value of A right here is A minus bracket A, which for those of you that don't know, that basically goes into statistics right there. The uncertainty of A is seen as the square root of bracket A squared bracket minus bracket A squared. And for those of you that know statistics, this is basically just a invariance to find. And from there, we also have the relationship that when we have the expected A times the ket of PSI, we get the relationship of X ket. And then we also have the same, the same also goes with the operator B. So from operator B times the ket of PSI, we get the ket of phi. And so, and also from there, when we get PSI, the bra PSI and the ket PSI, we get bracket operator A squared bracket. And so, and then on top of that too, this is important too, when A, because this is how the principle of uncertainty is derived from right here, is when A is the position vector and B is the momentum vector, the commuter is I h var, which comes from this equation right here. And that's plays a big deal because once we've substituted these into the Schwarz inequality, we have to then implement the commuter right here into it to finally get the result of the Heisenberg principle of uncertainty. And what I think is really pretty about this is from these equations earlier, from this one, what we can do is we can substitute the ket value for x, and we can write it as PSI A, and we take the Hermitian, we basically take the complex transpose of A for the first part, and then we do A, then we do PSI again, and then I'm going to walk over here, and then we do the same thing for B, is where we take phi B complex transpose, that's what that T sign's up there for. It's not just a regular transpose, it's a complex transpose. And then we take B again, phi, then we do greater than or equal to, and what we would write this as is bracket, we have the operator A times the operator B all squared. And then and these are all Hermitian operators though, which means that this right here is equal to A, the complex transpose is equal to A. So then we can rewrite this equation as PSI operator A squared, PSI times phi operator B squared, phi ket is greater than or equal to, and this is where when it gets we use this relationship right here. What's interesting about this relationship is that since it is Hermitian and this one is a commuter, this one's always going to be positive, while it's going to be positive or negative, this term right here. So that means we can rewrite this as the operator A times operator B is greater than or equal to half commuter of A bracket B bracket. And then from there we can square these, so we can write this as operator A times operator B squared is greater than or equal to 1 over 4 times A bracket B. And doesn't that seem familiar right there? And then from there, this is what I really like about this problem, is then we can then write this as 1 over 4 times A B. And then another interesting part of this is, remember this relationship earlier, well, we can use that to rewrite this as the operator A squared bracket times bracket operator B squared, which is greater than or equal to 1 over 4 for A, B. And we're almost there, and what we can then do is from these earlier relationships, we can write out bracket operator A squared. It's going to be this result inside brackets squared, which leads us to bracket A squared minus bracket A squared. Notice that the squared is after the bracket, and then, oh, that's actually plus because it's a minus there. Then we do minus 2A bracket, and then from this we can simplify, and then what we can do is we can then take the square root of both sides, so then we get bracket A is equal to, oh, and this ends up simplifying where one of these basically cancels out, so then we get bracket A squared, wait a second, yep, bracket A squared plus bracket A squared, and this is all under the square root, which then shows that the bracket operator A is equal to the operator A itself. And from that, we can rewrite this as the operator A squared, operator B squared is greater than or equal to, remember how I was talking about the commutator earlier, where we get the I h var? We can rewrite this as h var over 2, and that is the principle of uncertainty derived from these relationships. Oops, and I forgot to mention that since we implemented this from the operators, this would actually be rewritten as operator x, operator p is greater than or equal to h var 2, because you take the square root, and that's why this 1 4 goes into 2. So this would actually be 4 right here, and it ends up being the operator x, operator p is greater than or equal to h var over 2. And what I love about this problem is the overall, there's just so many steps to it, and it yields such an elegant little equation at the end. It describes so much in our world. It has absolutely changed the realm of physics, and physics will forever be changed by this simple, elegant relation derived from all this mess. It's all comes together in one beautiful little equation, which is what I love about this problem right here. Just this elegant equation. And I think it's so fascinating that they had to refine it through experiments first, and it was only until after that that they used the mathematics. Could you imagine if we would have used the mathematics in the first place, and we would have derived this, and we would have been able just to use the mathematics and then experimented on those specific values to derive this quickly? And that's just what I love about this problem, and what I love about mathematics in general is it has this elegant applicability in the world.